So
Okay.
next up, we have Dr. Hasnain. Doctor is a data scientist at NASA JPL System Engineering Division, where he leads research on autonomous space exploration, focusing on physics-informed machine learning and system health management, with experience spanning data-driven, probabilistic, and physics-based modeling across space, healthcare, and autonomous system domains. So take it away.
Awesome. Thank you. Can you guys hear me okay?
Yep, we hear you great.
Awesome. Okay, so yeah, first off, work I'm going to present is in collaboration with a couple other people at JPL. Rez Rahman, he's a thermal engineer and he's always interested in expanding his capability set, usually because they're under high pressure situations to turn around analyses really quickly for different missions. And Eric Bailey, who's a simulation expert, and he's kind of our local Dakota expert. Now, a lot of this work is influenced by his experiences as well. Okay, so the outline here is I'm going to talk a little bit about things which we probably had enough primers on, but why do we need UQ? What are the pain points and kind of where we stand right now? This talk is focused a little bit on the thermal engineering side of things, but it really is applicable to other aspects of modeling too. And then I'll show a proposed stack, and the motivation here is, there's some talks which focus on new methods and new techniques and novel ideas. This talk is more about, okay, so you're convinced that you should do some kind of UQ or optimization. What's the easiest way to get in the door and start actually doing it? That's what my motivation was. And the takeaway from today is I really want you guys to feel like there's a tool out there which we can all use, thank goodness. And it makes it pretty easy to actually execute some of these analyses. And I feel like unless you're a developer of a technique, we can rely on standard tools like this. So I'll explain what the proposed solution stack is. I'll give a couple of small, very basic examples and hopefully motivate people here to get their hands dirty with some of this stuff. And the motivating example that I'm going to use is this dummy satellite that I'm showing on the right-hand side. Okay, so why do we need meta-analysis tools at NASA, right? So there's a couple of common pain points that happen is that anytime someone needs to turn around an analysis, their first instinct is to write something up themselves, or maybe you go online and you search for some very specific analysis that you need to do, and you might find a different software package or Python package perhaps. And at the end of the day, you end up building something specific to your analysis, right? Now, everybody sitting to your left and right might also start doing that, and very soon it becomes a big mess, right? So the need here is to have consistency across different studies. I mean, there's work that's happening that we would have to cite that happened years ago, and there might not be any way to even access the software that was written at that time, right? So it's really imperative to have a consistent application and tie back to algorithms that we can all that we know are vetted when we're doing these types of analysis and we're asking questions like what is the optimal design, what is the sensitivity, and so forth. The other need here is that when you get down to the implementation side, we actually need a standard interface to all these different tools, right? So in physics modeling, there's so many different tools, but we need a standard interface to all these tools. So there's structural, thermal, optics, dynamics, whatever it may be. We need a centralized way to link to all of these when we start asking these meta questions, right? And the idea is we can have one interface and we can build that interface once, and then we can execute that interface as many times as we want to, right? And that would be something that gets inherited as best practices when a new team starts developing a completely different type of a model, right? As design evolves, but we want that repeatability there, right? And this is an area where sometimes we really lack repeatability. So if you focus in on one of the areas, right, you go to a structural engineering team, they might have their system really figured out and they have consistent practices. But then soon as you start linking with other teams and other models, things fall apart usually, right? So that's where we want to have repeatability. And it's so important when you're trying to actually answer these big questions. Oftentimes it's not the smaller details that get reported, it's larger numbers. And so it's even more important to not make mistakes. And one thing I didn't put in the slide is it's at that time where you've done all this work, you've built this model that's super sophisticated, you understand it, and now it becomes time to report something like a key metric out to, management, and you say, okay, I'm going to run a bunch of simulations and write my own metrics. That's when you can make a lot of mistakes, right? Maybe you didn't compute a metric correctly, and maybe it's not, calculated the same way across different teams. So we want to minimize those mistakes. And the next point is, okay, scalability. We have, anyone from interns to regular staff to other centers that are working on problems nationally and internationally. They may have access to large clusters. And so when you work on these teams, you quickly find that we're not all working in the same environment, right? And you need something that's cross-platform and you need something that scales with compute as well. And you really don't want to be license bound, right? So that's the holy grail usually of any type of simulation set that you're working with. And luckily, I'm talking, of course, about Sandy's Dakota tool, right? And luckily, it checks those boxes. And it's been available since 1999. I think the development started for it in 1994. So you want to ask yourself when you're sitting down to do these questions, to answer these questions, will you be able to build something that's going to match that level of heritage, something that's been tested for that long? And I would say, unless you're focused on building a new UQ or optimization or parameter estimation technique, I would lean towards relying on tools that solve these problems really well and that have been doing so for a long time. That gives you a flavor of why we need these tools, right? And what makes it difficult to actually implement these techniques. Okay, so now I'm going to shift a little bit to the thermal specific arena, right? So I work on thermal engineering, and again, you might have some of these problems even if you're not a even if you're not doing thermal engineering yourself. So thermal desktop, which is kind of our standard tool across NASA to do thermal analysis, heat transfer, and fluid flow analysis, it uses actually turns out it uses a solver called Cinda, which is written in Fortran. And so you've got this top shell layer that's, it's a GUI and you're building these models, but that actually ends up writing some Fortran and using the Cinda solver to compute your actual results. That's great, but the issue is now you need to actually, if you want to do anything like design of experiments, optimization, and all that, there is capability there, right? But again, this is that same point I was alluding to earlier, is that now you've got something that's very specific to your tool set. It doesn't link with other tools, and on top of that, you need even more niche knowledge to execute it, right? So you'd have to know Fortran, a little bit of Fortran. You'd have to know how Cinda works, which again is a niche product, right? So if you've already spent a lot of time learning your software, thermal desktop, let's assume in this case, and now you want to do UQ, your time is better invested learning a standard tool, which tomorrow, hey, if you stop working on thermal engineering, you work on something else, you can still rely on that tool set, right? You're not saying, oh, well, I used to use this Fortran library to do optimization. Now I work in optics. That library doesn't apply, so now I'm going to start all over from scratch, finding something else that does all these simulations for me, right? So you want to build knowledge over your career and know that it's going to be relevant once you switch projects. Okay, so what is Dakota? And I'm not a Dakota expert, so I'll just tell you what drew me to it and why we're exploring it as much as we are. So out of the box, you get methods for UQ, for sensitivity analyses, for optimization methods, both gradient and gradient-free methods. So that's really nice, right? If you're simulation doesn't actually compute gradients, which it very well may not, you can still do optimization, and that's awesome. The other really cool thing is you can build surrogate models, which is I'm going to use the word awesome again. That's awesome too, because if you're running a bunch of simulations with a high fidelity simulator, you know how costly that is, and you might have access to a cluster, but you may need to hand this model off to a design team or other systems engineering teams who are not going to be able to run a high fidelity simulator, but they still want to ask questions, they still want to query that model. So you can actually build a surrogate model by varying some of the key parameters in your high fidelity model and hand off that surrogate model. And while we're talking about it, I'll note one other point there, or actually I'll come back to this later in more detail. Um, the other really nice thing about Dakota again is it manages parallel execution. So, you know, you can, if you're used to using MPI, you can do that, Slurm and PBS Pro. Uh, all this, what this means is, you know, if you can develop something locally on your machine and you can know that it's going to scale up to a cluster, and that's a really powerful capability, which, to be honest, it's not, you can't say that for a lot of other systems, right? And finally, there's a lot of interfacing options here. So uh, I'll talk about this a bit more in the next slide, but why not do that? Well, actually, yeah. So you can use C, C++, Python, and so forth. I think most people probably fall into one of those first three categories there. So that's Dakota. It's owned by Sandia. It's open source. You know, you can find versions releases all the way back to 2001, which, you know, again, as I was saying, if you're gonna start writing these tools, you won't be able to beat that kind of heritage. So, okay, so that was Dakota. Now the other piece that I'm gonna wrap this around and show examples of the actual, you know, simulator in this case is Thermal Desktop, right? And uh, just real quickly, like, you know, very recently it used to be owned by CR Tech and now it's been acquired by Ansys. So again, you know, this should tell you, okay, well, I relied on one piece of software, it can change hands, but I don't want my whole tooling to break down if that happens, right? So it not that I'm implying it has in any way, but it's nice to be able to separate out your analyses if you can into something that's more long-term and reliable. The key point here is that Thermal Desktop has an API called OpenTD, and this is you can so using the .NET framework, but you can use any language that can talk to .NET. So it could be C Sharp, which is mainly what they use, but you can also use MATLAB and Python. So I'll be using the Python API for the demos that I'm going to show today, but just note that they don't have a lot of documentation for the Python API yet, so I had to do a lot of tinkering to do this. The takeaway for you guys here is if you're working in any other kind of simulator, ask yourself if they have an API, because Dakota will need to call your solver, right, somehow. So it would need some kind of API to be able to run your software. That might be a command line call, that's fine. But it helps if there's some kind of API like that, right? So the only thing it can't do is run a GUI for you. So if there's a programmatic way to run your software, that's all you would need. And luckily for me, in this case, Thermal Desktop does have an API. So what does the proposed solution stack look like? And I'll show examples of this in the following slides, but I wanted to illustrate how simple this is. At the very top is your input file. This is a Dakota script, and Dakota has its own language. It's pretty straightforward, and you'll see that. Hopefully, you get convinced today. And this calls your analysis scripts, right? And it specifies your analysis method, says, okay, these are your independent variables, vary them over some range. Here's your output variable that you're tracking. I want you to optimize that. And call this line here, call this function, run this, command line analysis to actually execute that software, right? So that's what's happening in this input file. And in the middle layer here is that function that Dakota calls, right? So in our case, for this example, it's a Python script. Uh, and the other nice thing is that Dakota has a Python API itself. They have a Python module. So it can read whatever the inputs are from that input file, passes on to another Python function, which then uses in this middle step here, the OpenTD Python API for thermal desktop, right? So now I've got my input parameters. Now I'm passing them along to thermal desktop, and I'm actually then running the thermal desktop simulation, and I'm outputting those results. And in the end, there's a Python script which kind of reads all your results and visualizes or it does whatever you want to do in post processing. Okay. So basically, just think of it, there's an input script, then there's your actual software that's running in the middle there, and then you can output to whatever format you want. It doesn't get easier than that. Oops. Okay, so the example that I'm going to show is this very simplified Earth orbiter. It faces the Earth. I've shown a very dense mesh here on the right-hand side to kind of show you what it looks like, but it has four main submodules, and I reduced the node count for this examples, but there's two solar arrays. There's a main section of the spacecraft, which is kind of this purple part of the CubeSat. And then the front side, which faces the Earth, is your optical bench. And so this might be a very sensitive, most sensitive part, thermally speaking, of your spacecraft, because you may typically want to mount instruments on that side. And then you have a protrusion on that optical bench, which is facing the Earth as well. So in a given system, obviously this is very simple, but in a complex system, you might actually care about the thermals of a very specific subset of the entire spacecraft, right? And that's kind of what uh, I wanted a model that's complex enough to illustrate that. So in this case, we're going to pretend that the optical bench is the most thermally sensitive area. And in our simulations, we kind of do one orbit, and each orbit is defined by a beta angle, which doesn't matter too much for this talk. But this is kind of my dummy simulation here. Okay, and so let's ask ourselves, let's try to do a few very common, very basic UQ and optimization simulations that we might want to do in our standard workflows, right? So the first two are sensitivity analyses, right? And you can do them in two different ways. You can do your Latin hypercube sampling, or you can do random sampling. Obviously, the benefit of random sampling, as you guys know, you're going to be able to get your overall trends without doing as many simulations. But you could use a Latin hypercube sampling if you really want consistent coverage of the input domain. And finally, I'll show an optimizing without gradients example, which I think is it's excellent to have access to something like that out of the box without writing that software yourself. And okay, so here's an example of on the left-hand side, I'm showing what that input Dakota script looks like. And the right-hand side is the output, and I'll get to that in a second. But let me walk through the left-hand side input script just to show you how simple this is. So Dakota has about 6 specific blocks, standard blocks that appear in their input scripts. And the first one is the environment, which just says, okay, how do you want to output this data? The second block there called method on line 7, that's where you're going to input whatever type of method you want. So I'm doing a sampling-based method. I want to do Latin hypercube sampling, and I want to do 50 samples. And then if you look down on line 15 at the variables section, I'm defining 4 variables that I want to vary, right, uniformly. So this is a thickness. So I'm going to vary the thickness of each of those regions of the spacecraft. The optical bench, the main submodule, the protrusion, and solar arrays as well. Why not? And the interface here is the part where you tell Dakota, okay, what are you actually running, right? And this is kind of the receiver. So it's going to generate some parameters, a parameter set for each of those 4 variables, right, that I've given it. And it's going to pass those along to this script called Python, sim sampling.py, right? And uh, you can give it the names of the input parameter file and all that. And actually, you don't even have to worry about that because if you use the Dakota Python API, it does the handshake between this input script and your Python script without you ever having to even look at an input file at all. And finally, the last section here is a response section, which says, okay, there's four response variables, right? And I'm telling you that I'm not generating any gradients or Hessians, right? Second order derivatives. And those, I'm just telling you the names of the four variables that I'm going to spit back out to you in the sim sampling.py file. In this case, I'm going to output average temperatures over all of those four regions. And the way you'd run this at the very top of this left-hand side window, I've just shown in this comment how to actually run this file, right? It's one one command line to run this, and it calls your simulation. It runs automatically. It opens up AutoCAD, closes AutoCAD. Um, Obviously, you have to do that with OpenTD, and I'll show an example of that in the next slide. But at the end of those simulations, right, it outputs something of a text file on the right-hand side here. I haven't obviously cleaned that up, but just wanted to show what it actually looks like. After it does 50 samples, it gives you things like your correlation matrices and some other statistics on your four target variables there. So takeaway here is look how simple this looks like on the left-hand side, and it's a good thing because you want it to be standard and something that's easy to read, right? And this is just a plain text file. It's not a complex GUI. It's not anything specific to a program. Okay, so now I'm showing you a snippet of that actual Python function that Dakota was calling, right? And so how do you set your model up to be able to allow Dakota to run these sensitivities or any other uh, analysis that you want it to? So obviously you have to expose something in your model to be able to do that, right? In this case, what did we ask Dakota to do? We said vary the thicknesses of each of those components of the spacecraft, right? So here I'm using the thermal desktop Python API called OpenTD to actually change the thicknesses of those areas, those regions of the model, right? And so this is a Python function which takes in values for each of those thicknesses, right? And here is the next snippet here is just opening a thermal desktop session, right? Uh, your code might look different if you're doing a different software, but this is, obviously specific to thermal desktop. And then this next few lines, I'm actually populating values for the thickness of each of those regions that are being fed into this function, right? So this call sim function is going to get inputs from the Dakota script. I didn't include those other lines of how it reads that because Dakota has really good documentation on how to actually write those helper functions. So there are two other functions here, which say get input parameters from the Dakota input script, and that's a standard Dakota Python function. And then there's also pack the results. So there's going to be some results that are generated out of this uh, that I'm going to post process, but then I'm going to pass those to a Python function that's standard to Dakota. So it helps you do the input and output there. And once you run that, right? I mean, this slide is basically just telling you about Latin hypercube sensitivity analyses, right? There's nothing earth-shattering here, but uh, just to drive this point home, the outputs you'd get like the moment statistics for each of those response functions, confidence intervals, and correlation matrices between inputs and outputs. So you'd want to post-process those, right? And generally speaking, you might not care about every single one of those outputs, but I made a list of questions here on the right-hand side, which you typically are asking yourself when you're doing this type of analysis, right? Like, okay, what is the probability of exceeding a threshold? What are the ranges of the outputs, right? Uh, what inputs actually affect the outputs? I mean, these are standard sensitivity analysis questions, but the point is you can get to this endpoint very easily and in a systematic way. And you'll thank yourself for doing it in a systematic way because, as we all know, as soon as you turn around one analysis, someone's going to say, well, what about that? And then you got to go back and do it again, right? So when you have to go back and do something again, you really don't want to have to develop some new code base. And that's really what I'm advocating for here. Okay, so that was okay, so yeah, so let me show you some results here. On the left-hand side here, for every single node in the spacecraft, I've just created a plot of the temperatures for one orbit. And that's cool, it's interesting. And but the main takeaway here is that, I never opened up Thermal Desktop and click run, right? This was all done programmatically. I never had to do anything for each one of these simulations. And since this is a Latin hypercube based sampling, on the right-hand plots, you can see the relationship between the thicknesses of certain areas to their average temperatures. And you can see it's a pretty dense sampling, right? So maybe we realize, okay, it's a pretty linear correlation here, but maybe we don't want to actually spend so much simulation time to generate these. So you can do random sampling. I won't go through this in detail again, but I just wanted to illustrate on the left-hand side this whole input file is the same as what I had before. The only line that I changed is line number 10, where I changed the sampling type from LHS for Latin hypercube sampling to random. That's all I did, right? And boom, you get your new simulations, right? And you can see the trends in the input and output variables that you wanted to see, and I'm able to run a completely different analysis without tweaking much of anything. Now ask yourself, if you had to do a Latin hypercube sampling sensitivity analysis versus random, you'd have to write at least a few lines of code, right? And I'm sure we're all capable of doing it. That's not the point. The point is we want it to be standardized so we're never having to write that again and again. And if you work in large teams, it's inevitable that we run into, oh hey, well, I do it this way, I do it that way. And rather I'd want us to focus on the post processing, and yeah, I'd advocate even standardizing that, but it's for another day. Okay, so I think I have a few minutes left, so I'll try to speed through this a bit. But this last example is an optimization one. And so here I said, okay, well, I want to keep the temperatures on that optical bench to be pretty even. So why don't I minimize the standard deviation of the temperature of each of those nodes in the optical bench? Really, you'd want to be minimizing the gradients there, right? But it's kind of a good stand-in for that. And again, the input file here, I want to iterate again. The only thing that's really changed is the method section, right? So now I've told it to use this pattern search, tell it how many iterations it's allowed to do, give it a convergence threshold for when to stop optimizing. And there is some obviously syntax that you would have to know, but again, they have good documentation, thank goodness. You'd expect that for a tool that's been live for a couple of decades. And so on the right hand side, you're seeing, okay, every single, and this is a Dakota output, for every iteration of this optimization, it picks out a set of thicknesses for each of the regions of the spacecraft, and then it outputs the standard deviation, the objective function that I optimized, right? And you can see visually here how it was able to reduce this standard deviation by looking for an optimal set of plate thicknesses for the spacecraft uh, in this search method, again, without any gradients or Hessians, right? So if I can go back here, at the bottom of this input script, I told it no gradients and no Hessians, right? So it's a gradient-free method. They also have gradient-based methods, of course, but I wanted to show the kind of simplest, easiest way. So the examples that I've shown you today, right, like sensitivity analysis and optimization, these are the most standard questions that you would have. And it's pretty easy to answer these questions using a very sophisticated tool, right, that has the heritage and you can rely on its analyses. Uh, of course, this is an example problem, so we're not really making an earth-shattering difference in the standard deviation, but that's besides the point. The good thing is we're able to get there and we're able to execute this analysis in a standard format, right? So uh, future steps, things that I would like, I guess closing remarks is maybe more of a would have been a better title for the slide, but I encourage everyone to read and download Dakota. They have a version that works for Mac, Linux, of course, and Windows, which is great, right? Oftentimes, when we're doing these mechanical analyses, we're license bound, platform bound. We don't have those issues here. And I encourage you to even write a dummy simulation script and try to wrap that with Dakota and see all the different analyses you can do. I think communities like this, we're all sold on the idea of these analyses, but either we lean towards building some very niche analyses because we have to, that's fair. But I think for the bulk of our work, we can rely on tools like Dakota, which are pretty standard. And I encourage you guys to look into or to find if there's an API for your tool. And if there's not, then I bug the developers of that tool to build an API. And trust me, I have been with Ansys and formerly CRTech. Luckily, they had one, right? But build an API if you have to do that yourself, and you can do that yourself because once you're able to do that, you can leverage all these standard tools out of the box. Um, there's obviously way more complex analyses. It's a state-of-the-art tool, which I think it's very hard for us to replicate that in our teams again and again, and we just would not want to do that in any case. So you can do cool things like surrogate modeling here. I wrote a blurb about that, but and finally, the last point I'll say is that even though in this case Thermal Desktop had some tools to do optimization and such, most of the times we're actually stacking these models together in a multi-physics or integrated model, meaning structural dynamics optics. So when you glue that entire train together, you want one wrapper around everything. Uh, so okay, I'll stop there. But thank you very much. Happy to take questions, and hopefully this was a practical takeaway for everyone here.
Thank you. We have a couple minutes for questions. Any questions out there? I have a question. So with AI tools becoming pretty good, probably help with interfacing between different codes and databases and et cetera. Has that influenced any of your thoughts on optimal sort of software stacks for doing this work?
Yeah, I guess you're meaning like, could I use LLMs to write some of these interfaces? Is that what you meant?
Yeah, or some sort of like agentic workflow of the AIs being,
Yeah.
talking to each other, controlling the different sort of disparate softwares.
Yeah, I mean, I think it's funny because I definitely did ask ChatGPT, hey, write me a Dakota script, and it wasn't really able to do that. So it's interesting because some of our analyses, some of our software is so niche, right? For all of us, it hasn't been fed into those models. But I think looking ahead, yeah, absolutely. There will be a day where we don't have to sit and write these input files even, right? And we'll be able to rely on these tools. So yeah, I look forward to that. Absolutely. All right. Thank you.
All right, thank you.